So you have this function and you want to find the max and min on a constrained domain using Lagrange multipliers. And that means you just use f gradient of f equals to lambda times gradient of g. And gradient of f is 2x, 2y, 2z. And gradient of g is 1, 2, and negative 2. So you end up saying 2x must be lambda, 2y must be 2 lambda, and then 2z must be negative 2 lambda. And then in addition to this, since you have x, y, z, and lambda 4 unknowns and only 3 equations, you have to include the constraint as your fourth equation. Only then you're able to solve this system because you have 4 unknowns and 4 equations. How do you solve this? Well, an easy way to do this would be solve for x, y, and z. So x is equal to lambda over 2, y is just equal to lambda, and if you divide by 2, you get z equals to negative lambda. These will go into this, and you get lambda over 2 plus 2 times lambda, and then minus 2 times negative lambda equals to 9, and this will become 9 over 2. Lambda equals to 9, so lambda equals to 2. Once you have that, you plug it back in, you get x equals to 1, y equals to 2, and z equals to negative 2 as some extrema. But the problem is we're trying to find max and min, so we're not really sure what this is. Is this a max or min? So that's when you actually have to think about the situation. See, this is a plane in 3D, and since plane is infinite, you can have points that are very, very far away from the origin. In other words, you can have x as very, very big. So you can have x as like 1,000,000, and of course, if x is 1,000,000, you can definitely find some y and z values which will enable you to satisfy this. Or you can even just say x is 1,000,000, y is 1,000,000, and solve this for z, and you get some value for z. So x and y and z can be as big as you want. Therefore, you can easily see that this will never have any maximum. So just doing trial and error, just plugging in some numbers and thinking, you see that the maximum does not exist. Whereas it's hard to make this as small as possible. For example, you can't have 0, right? If you plug in 0, 0, 0, you can't be 9, right? And because this is always non-negative, there is some value that's bigger than 0, which is a minimum value of this, okay? So we do see that there should be some minimum value. There must be some minimum value. And if that minimum value does exist, then Lagrange multipliers must be satisfied. And because of that, because Lagrange multiplier for us only gave us one solution, this must be the minimum. So this should give us a minimum value. And what is f of 1 to negative 2? That's 1 squared plus 2 squared plus negative 2 squared, and that's equal to 9. All right. So the answer, I should say, I'll just write answer in red. So the answer is max does not exist. Min, it's 9, and this happens at 1 to negative 2, which is not really needed because it wasn't asking for it, but sometimes it's good to know where it actually happens.